Okay, Bismillahirrahmanirrahim. So today we will be discussing about the pump. So how to design a pump for a water supply network and how to select the best pump for a water supply network and what are the different properties of water uh, of a pump. So based on that property, how to select a best pump for a water supply network. So there are two types of pumps: kinetic energy pumps and positive displacement pump. Kinetic energy pumps are those pumps which mostly used for providing energy or providing a head to a water, and positive displacement pumps are mostly used to move a water to from one place to another place, mostly concerned with the volume of water, not to provide a head to the water. So to transfer a water on a volume base from one place to another, so positive displacement pumps are used. So kinetic energy pumps, mostly centrifugal pumps, are used in a water supply network. There are three types of pumps of centrifugal pumps: radial flow pumps, mixed flow, and axial flow. Centrifugal pumps mostly consist of a rotating element called the impeller, which mostly provided the energy to the fluid in order to get to some place, to reach some place, or providing a head or pressure to that specific liquid. Consisting of the centrifugal pump consisting of a pump casing, which mostly gives the direction to the liquid to go through the impeller and then leads it way. Mostly the exact velocity of the fluid as it leaves the impeller tip is partially converted to the pressure. So mostly at the downstream of a impeller, a volute is connected to the pump. So by directing to that volute, the velocity converted into pressure means that the mechanical energy converted into the fluid pressure before it leaves the pump in the discharge nozzle. So discharge nozzle basically volute in order to give the energy to the fluid. The conversion of velocity to pressure occurs in the pump casing. Basically, in a pump casing, there's an impeller which convert the mechanical energy into the fluid energy. Pumps are often characterized by a type number known as specific feed, which varies with the shape of a impeller. So different type of a shape or different type of size of impeller have different type of a specific speed. So volute, most of the conversion of velocity to pressure occurs in the conical discharge nozzle. The size of the channel surrounding in impeller increases gradually to the size of pump discharge nozzle, and that diffusion basically the impeller discharges into a channel provided with the guide bands. The conversion of velocity to pressure occurs with the main passage. So this is basically the whole procedure inside the pump. So to discuss, discuss some terminologies related to the pump. So basically, pump is mostly provided in order to get water from the upstream and provide and reach it to the downstream with a higher providing at a higher elevation. So at the upstream side of a pump or or at a suction side, the difference between the center line of a pump and the water level of a water level is the suction left, while the difference between the water level of a reservoir at the downstream side and while the water level at the upstream side is called the static head, the static discharge head. Basically a static head and the static discharge head is basically the difference between the center line of a pump and the water level of a water or at a tank at the upstream side. And the total dynamic head is basically the sum of a suction left. The drawdowns occurs when the pump sucks the water to that pipe. The sum of the friction loss occurring through the pipe and the difference between the two, the level of the reservoir and the pump at the upstream side, is basically the sum of these two all heads is basically the total dynamic head. So each terminology is explained one by one. Capacity of a pump is the volume. So that how much volume of a pump can pump to the how much volume a pump can pump to the downstream side, and how much head it can give to that specific liquid in order to reach to specific point. So head is basically the elevation of equivalent free surface of a water with respect to a reference datum. So head is basically elevation of each point in a network, as we discussed in the previous class, of maybe the elevation head or the is basically the elevation of a junction or a pump, or the elevation of a water level in a reservoir. Pump head is basically the head provided by the pump to the liquid to raise the water. System head is basically how much head will be required in order to get some point by overcoming the elevation differences and the friction and minor losses for a given flow rate in a particular pipe system. Similarly, the static suction lift is basically the difference between, as I show you, the suction lift is basically a difference between the reservoir water level in the center line of a pump. Static discharge is basically the difference between the center line of a pump and the water level at a tank at the downstream side. So this is basically the static discharge head, and static head is basically the difference between the water level at the reservoir and water level at the tank at the downstream side. Total dynamic head is basically the head against the which pump must work when the water is being pumped. So it is the sum of the fraction losses occurring, the minor losses occurring to the pipes, the difference, the sum of static head, the sum of the suction lift. So these are different parameters to consider in order to design the pump, and basically pump are designed for the total dynamic head. Suction line is basically the pipeline typically leading from reservoir to a pump. This line will have, so basically suction line is basically this line moving from the reservoir to the pump, and basically at this portion the pressure is very low because this is suction. There is a suction pressure at that point at the suction line, and discharge line is basically the line downstream of a pump is called the discharge line. So pump efficiency is a very crucial and basic parameter in order to design the pump for a water supply network. So a good design should identify a pump or pump combination that operating efficiently to minimize energy requirements. So that type of pump should be selected for a water supply network that uses energy or the electricity efficiently without much losses. So therefore efficient pumps should be selected for the water supply network. So basically it is the ratio of output quantity to the input quantity. So in this case, for the pump efficiency, it will be the output power to the input power. In the context of pump, the quantity will be the power. So the goal of maximizing efficiency is to obtain the maximum power output for a given power input. It is basically the sum of three efficiencies: the pump efficiency, hydraulic efficiency, volumetric efficiency, and mechanical efficiency. Hydraulic efficiency is basically related to the pump casing, the different types of friction, eddy losses due to flow of separation and secondary currents occurring through that pump casing. Volumetric efficiency is related to the amount of water that passes through the pump components. And mechanical efficiency is basically the bearings or the friction occurring at the bearings or different type of mechanical parts of the pump, like impeller and the volute and the pump casing. So when the water moves through that, so the frictions occurs between the different parts of the pump. So the efficiency also depend on that as well. So it is basically the product of all these efficiency, and efficiency is basically determined by this equation Q gamma HP. HP is basically the power, the head provided by the pump, and P is the power, and it is divided by 550 in case of the US customary units. So pump characteristic curves is the basic property of a pump, on the basis of which the pump is selected for the water supply network. So this curve is basically provided to you by a manufacturer of a company for a pump by the pump manufacturer. So different type of curves are provided by the pump manufacturer: the efficiency curve, the head curve, and the power curve. So based on that, the designer designs the water supply network, the pump design for the water supply network. So I will show you, inshallah, the different types of curves provided by the pump manufacturers in order to design the water supply network. So this curve is provided to me by the Mr. Ataula. I'm very thankful to him to give me such to help me in such case. So system curve is basically very important property in order to design the water supply network. So so one is the pump characteristics curve, which is basically provided by the manufacturer, and other the system curve, which basically depend upon the depend upon the length of a pipe, the die of a pipe, as well as the tank provided in a system, the walls provided in a system. So the system curves depend on that. So basically, this is the pump curve provided by manufacturer, and this is basically the system curve. And the point at which these two curves occur is the operating point at which the pump operates and provided the head and discharge to the system. So the system, basically for this system, the system curve will be the difference between these two, the water level of a water in these two reservoir, and the head losses occurring through the through this pipe due to fraction, and similarly the head losses occurring to the minor losses occurring to the valve and the pump, etc. So we will do some example on that. So for example, a 6-inch diameter pipe connecting to two reservoir, a static length of 60 feet is a 250 long pipe for a pump with property shown below. So basically this is the property of a pump, the head curve and the efficiency curve. Determine the power delivered to the pump. So use Ghazi-Weisbach equation for friction losses and take a fraction for the pipe. The sum of all minor loss coefficient is equal to 30. So assume fully turbulent flow. So we will use this curve in order to design to solve this problem. So first of all, we will find the system head curve. The system head curve will be found by summing the the static left plus the head losses occurring through the pipe, the fractional losses, and similarly the minor losses occurring through the pipe. So by using this equation, we will derive a flow of water for a day, to derive a system curve or the system head for a different flow of water through the system, just by checking of this value in this equation. So this equation is basically derived by just putting these values in this equation. So we get this equation. So based on this equation, different heads are calculated by providing a q value by just putting a q value in this equation. So by getting a system curve, we can find the operating point by the by passing of system curve and pump curve crossing with each other at a point. So at a point which when a pump curve and system head curve passes each other is called an operating point. So this is a point at which the pump will operate by providing about the 1000 GPM. Projecting it to the x-axis will give you the capacity or the flow of water, and by projecting to the y-axis it will give you the head of a system. So head of a system is about 140 feet, and based on that you can calculate the efficiency of a curve as well. So just by projecting it to the x-axis, y-axis, and similarly by projecting it to the y-axis on the right side in order to get the efficiency of a curve. So the efficiency of a curve is about 80%. So based on this efficiency, we will calculate the how much power will deliver to the pump in order to operate and provide that amount of flow with that amount of this amount of head to the system. So by just putting the values, we will get this horsepower of 45.8 horsepower units. Operating range is performed basically in some cases there are some pumps also available which operate at different speed. So manufacturer provided ranges of a pump, provide a range that the value less than the 60% of a best efficiency point. Means the best efficiency point, and greater than the 120% of best efficiency point, the pump will not work properly. So therefore the ranges of a pump provided by the manufacturer that the pump should operate in this region in order to get best efficiency of a pump. So these are basically a different speed of a pump, it is basically a single pump, but it's a variable speed pump which operate at different speed. So therefore showing the different color of pump curves of having a different speed. So flow rates will fluctuate about design values. Prefer that flat pump efficiency curve. So mostly the when the curve is more flat, then it will provide a better result, a better efficiency for the pump to provide the head and flow to the water supply network. Typically, good performance may be expected between the flow rates ranging from 60% to the 120% of the best efficiency point value. And the pump manufacturer sometimes shows dash pump head curves to indicate performance is not guaranteed at a very low or very harsh flow rates. So these are basically equations, similarity equations derived by the Buckingham-Pi theorem. So these equations basically are used for defining or deriving a specific speed of a pump, and based on this specific speed, we calculate the discharge of a pump, the head of a pump, and similarly the power input of a pump. So these equations basically used by the manufacturer in order to get different type of a curves by using a different type of a speed of a pump. So this is basically the the discharge coefficient and head coefficient equation basically utilizes in order to get the specific speed of a pump. For a single pump operating in a given speed, Q and H are taken at the point of maximum efficiency. So therefore, always try to select that pump which having a maximum efficiency. So higher the efficiency, so higher will be conversion of our input power efficiently to the output power. So centrifugal pumps are mostly available in different flow rates and different specific speeds. So for the range of speed of about 500 to 3500, radial flow pumps are used low discharge at a very low pressure. So mostly having various low discharge or low pressures are required, so the radial flow pumps can be used. So mostly radial flow pumps are used in our houses in order to get to water from water supply network and raise it to uh, the tanks provided at the upper floor level. And mixed flow pumps are used having a speed of 3500 to 7500, mostly for the flow rate of greater than the 1000 GPM, and the exhaust flow pumps are used having a discharge greater than the 5000 GPM. So mostly for the water supply network, when, for example, if you want to draw a water from a surface water, for example, the surface water, so a centrifugal, axial centrifugal pumps are mostly used for the supplying of water to the community. While mostly in a case of a tube well or a well, we mostly use a submersible for submersible pumps. So basically, centrifugal pumps are not submersible pumps, so you cannot submerge it into the water. So when you submerge it into the water, so it will burn. So cavitation is very one of the phenomena in pumps. It should be considered, and a very important phenomena. It's a very important phenomena in order to consider and for the design of a pump or for the selecting of a pump in for the water supply network. So basically, it occurs when the pressure at the suction side, mostly in this case, at the suction side, when the pressure at this pipe decreases from the atmospheric pressure. So at the suction point, at this point, mostly the atmospheric pressure, there's the atmospheric pressure. So that the pressure at this point and this point are equal. When the water rises, the pressure decreases, and when the pressure decreases from the atmospheric pressure, the bubble created, it starts boiling, and due to the creation of a bubble, the pumps do not properly suck the water, and at the down and sobat concept that yung mic ban kita sa doza na connect eh. So at the downstream side, when these bubbles collapse, so it greatly affects the functionality of an impeller. So therefore, the pumps should be designed in such a way that the cavitation not occurs. So we mostly pump hawani that's called the cavitation. So it's basically the region of high velocity, high points in a line immediately upstream of a pump. In pumps, low pressure results in the formation of a water vapors bubbles followed by a sudden collapse as the bubbles are carried into the region of higher pressure. So basically at this point, the pressure is low. When it reaches to the downstream of a pump, the pressure rises. So due to a rise of pressure, the bubbles collapse and greatly affect the impeller of a pump. So sudden implosive collapse of the vapor bubbles often occurs when the great force that may result in the structural damage to the pump. So net positive suction head is also an important parameter to consider for the design of a pump. It mostly occurs just the upstream of a pump. The critical point within the C is basically the critical point within the pump, and A point is just upstream of that pump. And it is basically the difference between the pressure head at point A and the pressure head at point C, which is the critical point at the inside of the pump. So basically, it's a piezometric head required to move the water from a point A in the suction line to its point of a minimum pressure in the pump. So basically, the decrease of a pressure mostly occurs in this region and causing greatly affect the water, the pump. Therefore, the NPSH, the net positive suction head, should be such that it not causes the cavitation in the pump. So we will discuss a problem on that. So you will better understand on that in that problem. So preventing cavitation pumps. So mostly we choose the elevation of reservoir surface as the datum and the pump center line. So basically, in order to design a centrifugal pump, mostly in the case of centrifugal pump, so net positive suction head is basically the how much the pump should be placed above the surface of a water at the reservoir in order to avoid the cavitation. For example, if the NP, the suction left is about 1 meter, and you have placed the pump at about 1.2 meter, so it will cause a cavitation. And cavitation basically controlled by the net positive suction head. So this should be controlled. And the manufacturer also provided the net positive suction head for the pump in order to know that where the pump should be placed above the surface of a water in order to avoid the cavitation. So Y is basically a suction left, HL the all head losses between the reservoir and the head inlet. So this basically equation based on which the suction left is calculated, and in this the MPCH is the very important parameter in order to design a water supply or in order to design the pump or water supply network. So basically, when you have to design a pump, then the length of a pipe should also be not that much high, which causes the gamma is the unit weight of a water, 9.81 kilonewton per meter cube. It's basically provided a head is equal to P is equal to gamma H. P by gamma is equal to head. So basically this is the equation of head. So the length of a pump, the length of a pipe connected to the pump at the suction side should also be have appropriate length to avoid the cavitation. So higher the length of a pipe, higher will be the losses. So it will cause more chances of occurring cavitation at the suction side. So a net positive suction has basically provided the manufacturer to the designer, and based on that the centrifugal pumps are designed. So by preventing cavitation, so the net positive suction head obtained should be greater than the net positive suction head required provided by the manufacturer. So mostly the potential problem when pump discharge increases and decreases will beyond the rate of at the best efficiency point. So as I shown you the different curves, having manufacturer provide the best efficiency point of a 60% and similarly the 120%. So cavitation mostly occurs when pumps operate at this point or a pumps operate at this point. So therefore a best efficiency point a pump should be selected in order to operate at this region to avoid the cavitation and also provide a best output power or energy using a input power. So goal of a pump selection is to select the most suitable pump or pump combination for a given application, identify the operating point and associated conditions. So first of all, to select the pump, you have to find the design flow rates. What are the ranges of flows, maximum, minimum, average, for what period you have to design, what is the head capacity relationship between the head and the flow, design flow. So this the curve provided by the manufacturer. So this is the head capacity relationship. The net positive suction head. So basically this is provided for the non-submersible pumps. What are the efficiency, best efficiency pump should be selected, power providing to the pump and other relevant information on the pump. So these are the different steps to select the pump for the water supply network. So a preliminary assessment need to be made to determine what kind of a pump is suitable for a given application. So first of all, you have to find the Q required for the system, and preliminary analysis of water distribution system, which we will do in a WaterGEM, and based on that we will determine the flow and also calculate the pump head required in order to reach the water from the downstream, from the upstream to the downstream of some level. Based on the value of head Q obtained from step 1, assessment can be made as to what type of pump is suitable. So from the pump head curve, we will decide that which type of pump should be selected. So we will also calculate the system capacity, the system head required for the system, and based on that we will check the different pump characteristics curve, and based on that pump characteristics curve we will decide that which type of pump should be selected. Matching pumps to the appropriate motors, chart supplied by the manufacturer. Select the appropriate region or flags. I will show you the flags. So basically different regions are mostly different type of curves are provided by to you by the manufacturers, and each curves range of curves are denoting through some flags number. So based on that flags number we will decide a specific specific pump or curve for the water supply network. So it basically refers to the specific pump speed or the specific pump. The region covered by each flag defines the operating ranges of head discharge values of that pump. The various regions with same number correspond to the same pump operating at different rotational speed. So this is basically the total head and capacity curve. So what you did, you draw a system curve, and based on that you take the different flags, and based on that flags you select the appropriate pump. So these are the basically the different curves related to specific flag number having a specific speed and size of a section or of a impeller in a pump. So these are the different curves based on which a pump is selected. So these are just given for the demonstration purpose. So basically I will be using these curves in order to design the water supply network, design a pump for a water supply network. After step 3, what you will do, you will find the system discharge curve by finding the flow rate through pipes having losses, minor losses, fraction losses, the difference between the water level in the reservoir and the most higher point at the downstream side. So based on that, the pump will be decided. So for each chart, the intersection of a system curve with a, so these are the assumptions which I have explained in the previous slides. These are the different curves referring to the specific flag number which provided to you by a manufacturer. And the final choice is selecting the best efficiency and the pump having provided the flow rate, the flow to the system which is required for the system, and the operating point with the lowest net positive suction head required to prevent cavitation is desirable. So we will do a problem on a net positive suction head. So in this problem, a pump is basically transferring a water from a reservoir 1 to the reservoir 2, having a difference of static head of about 50. Put the static head is equal to the 50 foot. The length of a pipe is about 800 foot, 800 feet, and the diameter of a pipe is about 10 inches. The friction factor of a pipe is about 0.015, and sum of all minor losses occurring to this pipe is about 6. To select a pump from the given choices and determine operating condition. So operating condition will be determined by drawing a system head curve. If the total losses in the suction line is 2 times, velocity head, what is the maximum allowable section left to prevent cavitation? So basically, we are supplying the water. So this suction left, we will calculate the suction left to supply a water to a suction left for a pump, that how much the pump should be placed above this level of water in order to avoid cavitation. The flow is given, the static head is given, the length of a pipe is given, diameter is given. So based on that, we will calculate the velocity. Friction factor is also given. So these are the given values. Based on that, we will calculate the system head using this equation, as I have shown you in the previous slide. So this amount of head is required basically. So this equation basically generally we will use in order to select a pump for our water supply network. So now we will derive a system curve by putting a discharge equation in place of a velocity. So basically this is the velocity. So Q is equal to AV, Q by A is equal to V. So this equation basically put in this equation in order to get the system curve. So by putting the different flow rate values in this equation, we will get the head for the different discharge value. And by plotting in Excel, we will get a curve in the form of this, like this. So what you will do in order to select a best curve? So what is the flow rate of a system given to us? It is about 1700 GPM. So we will project this value to the pump. It is somewhere in between, like it will select, it will this, okay. And then project it to the y-axis, and similarly project it to the in the upward direction, and then project to the right side at the y-axis. And from the curve you can observe that it have efficiency, it required of efficiency of 73% of the curve. So we get different type of values from this curve of net positive head of 30 feet, if of about 30 feet, and similarly a pump of 73% of efficiency is required, having